with me. Good morning, everyone. First, I want to apologize for not being able to come to class last Thursday. So we're going to pick up where we left off. Also, I just realized that I have not uploaded the video from last Tuesday or this Tuesday. So I will make sure and get that done tomorrow morning so that you will have all of the lectures we've done so far over the solar system. But I'm going to continue on today because I'm assuming that you have looked over chapter 7 in your book, which is where we have been and have gotten up to this point. This is the only section of the course where I don't teach directly by the chapters. However, the homework assignments, assignment 7, 8, 9, and 10, are still directly along with the chapters. But I just make sure you get all the information that you'll need. So I'm going to continue where I left off in Tuesday's lecture. So we had passed by the inner terrestrial planets and discussed them. We made the long distance and finally got 9 astronomical units out from the sun to reach Saturn. We discussed Saturn and its rings. We talked about its moons a bit, especially Titan, its largest moon with a thick atmosphere. I also want to mention Hyperion, which is one of Saturn's moons. It's a very weird looking, kind of looks like, I don't know, maybe it was molten at some point and gases escaped from it. We're still trying to figure out why it looks so unique. All right, but that's just as we move further out to Uranus. Now, if you see this image of Uranus, it looks like just a blank greenish blue ball. And most of the images of Uranus do look like this. It's kind of featureless. Not really, but kind of featureless. In this image, I believe we're looking at Uranus's south pole, approximately. But you can see by size comparison, it is much larger volume-wise than Earth, and also much larger mass-wise. So Uranus is the first planet that was actually discovered. All the other planets before this, you can see with your naked eye, so they've been known throughout all of human history. However, Uranus can not, and only on the rarest circumstances, be seen with the human eye. So it was discovered using a telescope by William Herschel in 1781. And an interesting point about Uranus is its axis of rotation lies in its plane of orbit, which means it looked like it fell over. Which is why in this image, as stated, the south pole is about right here. There you go. First, that blue-green color is because of the methane clouds that make up its cloud, the visible cloud layer. Another interesting thing about Uranus is it has 15 moons, approximately. I think there might be a couple more that I need to update. But of all of the moons that Uranus has, they're all super, super dark and not very reflective at all. And in fact, only 5 of them can be seen from Earth-based telescopes. I mean, if you pull out a super strong telescope and look at Uranus, you're only going to see the 5 largest ones, the round ones. Any of the other ones, you'll need a very telescope above our atmosphere. Uranus, of course, has rings, as all of the Jovian planets do. Of course, as stated, Saturn has the most robust ring system, but Uranus does have rings as well. You'll notice that they are around Uranus's equator, which is this way. So they have this orientation. Again, in this image, the South Pole is about right there, if I'm not mistaken. Wait, no, hold on. Make sure I'm right. In this image, this might be the North Pole. Yes, the North Pole right there. So all of the moons and the rings orbit around the equator, which give a really interesting sight. But the rings were first discovered using what's called stellar occultation, which means a star was hidden. Occultation means to be hidden. So as we orbit around the sun, our position relative to Uranus changes. So we would see a star that was right here disappear, then reappear, then disappear, reappear, disappear, reappear. And well, okay, why is that star blinking? That's weird, right? Stars don't just randomly blink. So of course our first question was, is this some sort of signal, right? And eventually we're like, okay, that's not some sort of signal. It's a pattern that all stars have when they're near Uranus. They blink off, on, and then off, and then back on. And so, of course, using those patterns, we were able to make a shape, and the rings were the shape that were around Uranus. And of course, we were able to observe them visibly later. But at first, it was just that weird flashing pattern that we saw. Here's another image. This one's a better image. This is not quite true color image, but moderately close. You can see the outer rim of the upper atmosphere here. It shows the rotational direction of all of Uranus's moons and the rings. And they have names of Shakespearean characters such as Cressida, Bianca, Puck. But as you can see from this image, the rings are more robust than, say, Jupiter's rings or Neptune's rings, but of course not to the level of Saturn. Pretty cool. When I first learned a lot about Uranus, I was like, wow, this place is boring. It doesn't really have anything special about it. Of course, then I learned about its orbital orientation, and I thought it became cool at that point. But let's keep moving throughout the solar system till we reach the final and most distant planet, which has an average distance of 32.1 astronomical units away from the sun. Yes, approximately 32.1 astronomical units away. Neptune! Yay! Neptune has a similar bluish color to Uranus, but it's a deep blue. And when we first found Neptune, it wasn't that we found it, it's that calculating Uranus's orbit led to some weird perturbations. We're like, well, another planet could cause that if the planet is all the way out there. And so we looked. We looked at the predicted place. Remember, one of the qualities of science is its ability to predict phenomena. And we were actually able to locate this planet based only on the predictions of Uranus's orbit. So it was the next discovered planet. Again, it's blue because it has those methane clouds in the visible cloud surface. But Neptune has a lot of other interesting features that you don't necessarily see on Uranus, such as its great dark spot, which is right here. This is a constant storm that's always on there. These little white puffs here are white clouds above the surface. You also are able to see some banding that you see on most, that you see on most of the Jovian planets. Sometimes Neptune will have like a little green band that appears down here in the southern hemisphere, but it's not constant. And of course, Neptune has very, very faint ice rings. They do exist. There's a close-up picture. So this blue color, we're going to call that the quote-unquote surface. It's not really a surface. It's just the visible cloud layer. And these bands here are also at the same altitude. These white clouds here are higher than that, above the surface. Now, the interesting thing about Neptune is it does have, I want to say 8 at last count moons, but most of them are just captured comets that maybe passed too close. Especially Triton, which is Neptune's largest moon. Triton is the only large moon in the solar system that orbits around Neptune retrograde. But Triton is Neptune's only round moon, or only spherical moon. Here's a picture of Triton. With the most scientific area ever, the cantaloupe terrain. That's right. You're just like, that looks like a cantaloupe, so let's just name it cantaloupe terrain. It's also got some dark wind-blown deposits, which means it does have a very thin atmosphere, or else there wouldn't be wind there. But it has a very interesting surface features and shapes that we don't know too much about it. We're not sure why it has this weird cantaloupe shape. It's thought that maybe part of the atmosphere evaporates and then re-solidifies, and it just has this weird pattern when it solidifies. We're not sure. But it looks cool, though. Okay. So that is all 8 of the planets. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. We reached them all. So now that we have taken the time to visit all of the 8 planets of the solar system, we want to start finding out, okay, what does this tell us about the solar system? What can we know from the planets that we have passed by? We know they exist. We want to start trying to look into why, making some hypotheses about possible formation, and see what kind of tests we can do. On this image here, I have all 8 planets by relative sizes. Not relative distances, obviously, but by relative sizes. Here's Mercury up here. You can barely see Mercury. And you start comparing Mercury to the size of Jupiter, and, well, that's a big difference, right? Or maybe you compare Saturn to the size of Jupiter, and you're like, okay, this is about 2/3 the size, or maybe 80% the volume. But then you start thinking that Jupiter is 3 times more massive than Saturn. And in fact, as stated in one of my previous classes, Jupiter is twice as massive as the rest of the planets put together. It's big. I think Jupiter could actually hold all of the planets, not all of the planets, but any of these other planets except for this one, and maybe this one, in orbit around itself. Just one of them, maybe. I don't know. But it'd be interesting to find out. So let's look at these patterns and talk a little bit more about the formation of the solar system. What we see are clear patterns of composition and motion. What do I mean by that? Well, what we notice is that large bodies in the solar system have orderly motions. Here's my sun right there. And then you'll notice that each one of the planets orbits around the sun counterclockwise when viewed from the sun's north pole. Right here. Venus, Earth. Well, they all orbit in that counterclockwise motion around the sun's north pole. They all have nearly circular orbits. Mercury's orbit is less circular than most of the others, but they're nearly circular. All of the large planets orbit on the same plane, approximately. We call that plane the ecliptic. Everything I'm saying right now is approximate. It's not exactly the same plane, but approximately the same plane. Most of the large moons, with the exception of one, orbit around their planets in that same counterclockwise direction. And all of these are orbiting in the same direction as the sun's rotation about its own axis. The sun also rotates counterclockwise around its own axis. So that's a pattern. Doesn't necessarily tell us anything yet, but we can start thinking about it. Also, we notice that planets fall into two major categories. We got smaller rocky planets, Earth, Mars, Venus, Jupiter. And then we've got larger Jovian planets, Saturn, Jupiter, Uranus, and Neptune. Now, each one of these planets has its own trivia that's different about it. But if we're talking about major categories, we've got two major categories. That's a pattern. What does it mean? We're not sure yet, but right now, you can see it's a pattern. Next, there are swarms of asteroids and comets in the solar system. We'll start looking into those a little bit later, but right now, just rest assured that there are a lot of them. And even though there are quite a large number of asteroids and comets, they're concentrated mainly in three distinct regions, which we'll talk about a little bit later. The asteroid belt, the Kuiper belt, and the Oort cloud. So we know that there's a lot of this stuff. So the question then becomes, okay, how come it's concentrated mostly in these three regions? Again, another pattern. And now, for the most important part of the patterns of composition and motion. There are several notable exceptions that don't follow what we expect. Any hypothesis of formation or any hypothesis about the solar system must allow for the things that don't fit in the pattern. For instance, please look at Uranus and how it has fallen over, quote unquote, and how it rotates on its side. Any formation or hypothesis we come up with must allow for exceptions like this. We have a relatively large moon. In fact, comparing our moon to the planet, it's the largest planet. No, it's not. It's the second largest planet-moon ratio after Pluto and Charon. But our moon has 1/4 of our diameter, which is huge for a moon. Now, Jupiter is like this big, and Ganymede is about this big. So even though the moon, Ganymede, is much larger than our moon, the planet-to-moon ratio isn't as large. One of the mistakes I often see when people start talking about this portion is they say that we have the largest moon in the solar system. That is not true. We do not have the largest moon in the solar system. In fact, our moon is the 5th largest moon. Interestingly enough, Earth is also the 5th largest planet. Pretty cool, right? But whatever hypothesis we come up with must allow for these exceptions. Let's see. Venus rotates on its axis the opposite direction of the other planets. Any hypothesis we come up with must allow for that to happen as well. So take care and not ignore these exceptions. Taking a step back, I just want to say planets are very tiny compared to the distances between them. This will help us once we start looking into patterns of motion. If we got the sun right here, then Mercury, Venus, Earth, Mars, no problem. But then there's this large gap until we get to Jupiter. And then there's a gap that's slightly larger to get to Saturn. And then slightly larger to get to Uranus. And then a lot larger. This is, again, why it's really hard to make a model of the solar system that's to scale both as size and distance, because the distances between them start getting real big. If you go to Washington, D.C., there is a very large combination of monuments. This one's the sun here. It has sun information. And then you walk a few steps and you've got Mercury. Mercury, there's like a little arrow pointing to like a little super, super small dot. It was hard. It took some space to make it. In fact, Pluto is at the edge of the Arts and Industries building. I don't know if you've ever been to Washington, D.C., but goodness gracious, this is a long way away. Right? You're going to be tired by the time you get to there. But the important part is that there's a lot of space between planets. Looking down at a top-down view above the solar system's north pole, in the inner solar system, you can see the scale of the orbits of the planets. The diameter of Mars's orbit is approximately 3 astronomical units. You can see that there's parts where Earth and Mars are closer together, or you can see where there's parts where Earth and Venus are close together, even though they're pretty much about the same distance from each other. You can see parts where Venus and Mercury are close together, even though that's not perfectly correct. But then we have to zoom out even further and start looking at the other planets' orbits. If we take Pluto into account, then we've got a diameter of approximately 80 astronomical units. That's big. You may also notice that there are a few years here when Pluto was closer to the Sun than Neptune. That'll happen again in another 200 some years. 249 years, I believe. I'll remind you before it happens. Okay. One thing I have ignored talking about so far is the sun. Allow me to first say that the sun is huge. If you took all of the other stuff in the solar system and then multiplied it by 1,000, so all the planets, all the asteroids, comets, everything else, and multiplied it by 1,000, you would approximately have, not quite, the mass of the sun. And remember, Jupiter is twice as big as all of the other planets. So take all that, multiply it by 1,000. It is made mostly of hydrogen and helium gas in a plasma state. I say gas because most people understand gas better, but it's in plasma, which is the fourth state of matter, a little more energetic. The sun is so massive that it converts 4 million tons of its mass directly into energy each second, and it's fine. Like, it's just whatever. I'll keep doing it. And it's been doing that for about 5 billion years. And it's got enough fuel to do it for 5 billion more years easily. Here's a size comparison for you. This is the sun, and this is a solar storm called a prominence. And sometimes the sun, because it's so massive and energetic, the magnetic field of the sun just like flips out and goes woo. And when it does that, part of the sun's mass follows the magnetic field line. So this is a physical thing that actually happens. And I put the sun there, or the Earth there, just for size comparison, so you can see the size difference. So a random storm event on the sun just dwarfs the Earth. It's large. These are sunspots. These sunspots look dark because of the heavy filters that we've put over the sun. They're just areas that are slightly cooler, say 5,000 Kelvin, as opposed to the 6,000 Kelvin of everywhere else on the surface. But they're not actually dark. Again, let me reiterate, it's huge. Okay. So here I have a recap of the terrestrial worlds. Mercury, we got steep cliffs and craters. Venus, we've got, of course, these colors aren't real. Earth, we got all kinds of stuff here. The moon's surface sucks. It's basically just like a cratered, barren wasteland. The colors here aren't real either. BT dubs, the moon is not gray. We've got Mars here that has interesting features. So we see all these interesting features, and we could spend hours talking about the trivia. I could tell you about cool features that we found on Venus, interesting forests we found on Earth. But that's not as important. What's important are the patterns. What do we see commonly between these terrestrial worlds? Here, I just had a brief recap of all of the planets. So I'm just going to go through this very quickly, since I'm going to be putting up a lecture of that tour. Venus, close to the sun, made of metal and rock. It's got a large iron core, hot during day, cold at night. Venus is super hot, about 900 degrees Fahrenheit, atmospheric pressure 90 times that of Earth, sulfuric acid clouds, sometimes it rains sulfuric acid. It's about the same size of Earth, except it's terrible. You can't hang out there. Earth is awesome. We live there. Here, right over there. It has the only surface liquid water in the solar system. Able to have surface liquid water not only because its temperature, but its atmospheric pressure. Water is a really weird element that does not like to stay in a liquid state. It prefers to be a gas. But if it gets cold enough and has enough pressure, sure, it'll be a solid. It'll stay liquid if the pressure is perfect. There's Mars. It's reddish. It's got a lot of landscape features and dust storm weather patterns. Most of the images we show of the other planets show a very uniformness, where Earth is more varied. The planets have some variations in them as well. We just don't have as much information on it because we don't live there. Okay. Here's cutaways of planets where I just show the insides of the planets. We find that they look moderately similar, especially Venus and Earth looking very similar. Mars and Mercury looking relatively similar, except for this weirdly large core in Mercury. All right, going out to the Jovian planets, I know we just talked about these, so I'll give a very brief rundown. Jupiter's real far away from the sun, no solid surface. It's big. Got a lot of moons. Io, Europa, Ganymede, and Callisto, each one of those moons were in orbit around the sun instead of Jupiter, could be considered a planet. They're all moderately large. In fact, Ganymede is the largest moon in the solar system and is larger in size than Mercury, the planet. The Saturn, big, gaseous, also got a lot of moons, got pretty rings. We just talked about Uranus, so I won't go back there. And then Neptune, I won't talk too much about it either, since we just mentioned it. If we look at the insides of planets, you'll notice that Jupiter's and Saturn's very, very, very similar. Uranus and Neptune's also very, very similar. And all in all, together, they're similar. So we're just trying to recognize patterns. This slide here, to me, is one of my favorite slides. It shows the axial tilt of all of the planets relative to the axial tilt of its orbital plane. We got the sun here. Next, we've got Mercury. Mercury's rotational axial tilt is 0 degrees. I expect this, right? It's very close to the sun. I expect that its rotation would be oriented perpendicular to that. Next, we've got Venus. I would expect it to have an axial tilt also very close to 0, maybe 3.5 degrees at max. Turns out its axial tilt is 177 degrees, so it's upside down. But if it was upside down like 3 degrees more, it'd be perfectly upside down. And that, to me, seems like it would fit, right? Because as close as it is to the sun, I expect it to be rotating perpendicular to its orbital path. So it's weird that it's upside down, but it's not like that weird. Next, we've got the Earth with its 23.5 degree axial tilt. Yeah, I don't see anything too strange about that. It is getting a little further away from the sun, so I wouldn't expect it to be perfectly perpendicular with its axial tilt. And we do have that larger moon to stabilize that, so okay. Mars about the same as Earth. Yeah, I can take that. Next, we've got Jupiter. Notice that Jupiter is at 3.1 degrees, meaning that it's slightly off from its orbital path. I expect it to be lower because of its size. Saturn, 26.7. That doesn't say anything too special to me, but I wonder why. Wonder why it doesn't have a similar axial tilt to Jupiter. Uranus is insane with its 97.9 degree axial tilt. This is one of those things that we have to account for. Why? Why does that happen? And of course, please check Pluto and its 122.5 degree tilt relative to its orbital plane. Of course, Pluto has a unique orbital plane, so I was just showing that one because it's funny. Okay. Again, doesn't really matter that we have all these numbers. Not necessarily. We're looking for a pattern. It's also important to know that space itself is not empty. You'll find more raw gas in interstellar space, meaning the space between stars, than you will in interplanetary space. That's the space within solar systems or star systems. And within the solar system, most of the gas has been either drawn into a planet or the sun or somewhere. So it tends to be emptier than once you get outside of the sun's sphere of influence. There you find more stuff. You'll also know that the composition of space changes based on events that have occurred. And all of this information is just helping us build towards these clear patterns. So we need to start trying to figure out, of all of that information that I've said, which I've said a lot, which of those informations What part of it tells us or helps us find how it was formed? Which patterns are important? What matters? Which compositions were important? And of course, generally this is on a different day of the lecture, but I just wanted to show it again. You see all the planets orbiting the same direction. We see two types. We see all the smaller bodies and those notable exceptions. Okay, so in order for us to form a hypothesis that begins to attempt to explain the formation of the solar system, since that's where we're going, we got to get all the evidence we can from multiple sources, meaning from all planets, moons, comets, and stuff. We need multiple sets of information. We need to be able to integrate all those observations and any models that have been created, meaning that we would use the information that we have, the physics that we have, create computer simulations, possibly, and see if they allow for the solar system to end up where we are now. But there's a problem. When I say a problem, I mean scientifically, looking towards the formation of the solar system, there are quite a few problems. And let's talk about some of those. You can never, ever prove any theory or hypothesis correct. Ever. Right? Let's just say we found the exact way that the solar system is formed. How could we prove it? Well, in order to prove it, you would have to go back in time and verify it against what had happened. And not only that, did your going back in time change it? It's impossible to prove a theory. We can, however, disprove any hypothesis. And our entire goal in science is always, please check this out, our entire goal in science is always to disprove every hypothesis except the correct one. The solar system was formed from mashed potatoes. That's my hypothesis. If I can disprove that, then yay, I know that's not true, right? So I'm now closer to the truth. The solar system was formed from, I don't know, some other random thing. Okay, disprove that. Attempt to disprove it. If I can disprove a hypothesis, I'm now closer to the truth. So we want to circle around the truth, leaving only the truth, because you can't prove a hypothesis scientifically, but you can disprove them. I don't know where the solar system was formed from mashed potatoes came from. It's the quickest example I could think of. Another issue is we only have one example to study, meaning that we have one solar system, which could cause us to overgeneralize. We figure out how our solar system was formed and assume that other solar systems are formed that way. So we're overgeneralizing. Or maybe we find a way that our solar system formed and say that, oh, this is specific, it had to happen, which might not be the case. Or let's just say there are 85 quadrillion ways to form a solar system, and our solar system formed in one of those ways. So that would cause us to, again, overgeneralize. And also, any hypothesis that we discover is specific for our solar system, which should tend towards generalization, but we have to be careful to not assume that this is the only way it could have happened. So again, just so many questions, and we need to be aware of all of these things, because if we ignore one of them, it dilutes the strength of our scientific findings. And my favorite part about astronomy is the science part. So let's talk about the nebular hypothesis. The nebular hypothesis is going to require a lot of physics concepts. And according to the nebular hypothesis, our solar system formed from a giant cloud of interstellar gas called a nebula. First, in order for us to even begin to look at this hypothesis, nebula, or large gas clouds, have to exist. Luckily, we have seen them. We've observed them. We know that nebula are real, so we can continue with the hypothesis. Because if at any time, any part of the hypothesis is deemed false, then the whole thing is false. We gotta try again. So let's start with a very large cloud of gas. Let's give it a diameter of approximately 1 light year. Seems big enough, right? The first question would be, okay, if it starts off as a large diffuse cloud of gas, well, it's going to get smaller. It's going to be a solar system. Why would it contract? What physics principle would cause it to contract? Well, the universal law of gravitation says that the force of gravity betwixt any two objects is equal to the mass of object 1 times the mass of object 2 divided by the distance squared times the gravitational constant. So this means that all material, all matter, is gravitationally attracted. So this should cause the materials to begin to attract to each other and therefore contract. Okay, good. So far, our hypothesis is possible. We're not saying it's true yet, but right now it's possible. Okay. But we know that our solar system is not a giant cloud of gas and dust, so why would it flatten? Why would it start to spin? Well, the initial cloud of gas and dust had some very minuscule, imperceptible rotation. And you might be thinking, well, that's a large leap to make there, Mr. Palmer. Every molecule, or excuse me, every element that exists, every particle has an inherent spin to it. That's one of the quantities. So even if the whole thing wasn't rotating on average, every particle has a spin. So there is some spin to the nebula. And spin and rotation are different, yes, but for now. So there was some rotation speed. And one of the things we know is that angular momentum is conserved. So no matter how large or small this nebula gets, it must have the same angular momentum. However, if it gets smaller, in order to keep the same angular momentum, it must rotate more quickly. Why would it get smaller? Well, gravity's causing it to contract. So it's contracting, getting smaller in volume, which means its rotational velocity must increase. So it has to start spinning faster. Okay, so now we've got a shrinking, spinning cloud of gas. Okay, so it's shrinking and spinning, but you notice we don't have a giant spherical spinning solar system. So why would it flatten out into a disk? So as the particles begin to rotate or revolve around the center of the cloud, let me take a second here. The center of the cloud is not the center physically. The center of the cloud is going to be the area with the highest density. So all of the smaller particles are going to begin to orbit around the part with the highest density. That is your center. And as those particles of gas begin to orbit around the center, they're going to collide with each other. And those collisions within the rotating disk are going to even out the motion. Let me draw that. It's not going to be pretty, but I'll do my best. We're going to say this is the center. And we've got this particle orbiting this way, this particle orbiting this way, right? But let's just say they meet right here. The resulting motion of both of them is going to be a motion that is more similar, right? The resulting motion of both of them is going to be a motion that's more similar. And as they keep rotating, they're going to hit each other again. Let's just say they've gone back around, and then one of them's right here, and one of them's right here. And they've got the subtle. They hit each other again. Now their resulting motion is closer to the average. And upon repeated impacts, the resulting motion is going to be some average motion. So it's going to be working towards the average motion of all of the particles in orbit around it. Now, a lot of times people think of it like a pizza dough. Like you take a ball of pizza dough and you spin it and it flattens out. That is not what's happening here, right? Yes, that flattening out is because of angular motion, but that angular motion requires there be like a big force of gravity downwards so you can spread it out. This is not what's going on here. This flattens because of collisions within the rotating disk. It's still due to the conservation of angular momentum, but a different part of it. Okay, so now we've got a shrinking, spinning, flattening disk. This is starting to look like a solar system. Not quite yet, right? It's still a cloud, but it's a spinning, flattened cloud. And of course, this app has not run in years, so we're just going to skip over it. Okay, so we end up with planets. Where did all these planets come from? Well, remember, this is made up of a cloud of gas. So all of this is stuff. Remember, all of these particles have gravity. The densest part of the cloud is in the middle, the densest here. But that doesn't keep the rest of these particles from having gravity. In fact, to the dot, there's another dot there. Each one of those dots have gravity. Let's just say they get close to each other. Now you got a 3-dot group. That 3-dot group has more gravity than the dots around it. That's now another source, right? Something can fall in here, or it could fall into this little group here, or this group here, or this group over here. It's going to start clumping up. Also, when material collides with each other due to its angular momentum, it might stick together. So combining gravity, static electricity, remember opposite charges attract, and accretion. So this little source of gravity might cause a particle to start to orbit around it, and then it will spin together, creating its own accretion disk. An accretion disk is the disk of swirling material that begins to coalesce and combine. So because these particles are clumping up, we're going to get what's called planetary seeds or planetesimals. What's so different about the quote-unquote planetary seed in the middle? It has the most. This has the most. This has some, this has some, this has some, this has the most. And remember, the more massive a planetary quote-unquote seed is, the more material it can begin to accrue, because gravity. Okay, so how come it's so hot towards the center of it? Why is there so much heat located towards the center of that solar nebula? Well, conservation of energy. The total temperature of that nebula must remain constant. The total temperature of the nebula must remain constant. Conservation of energy. As the nebula begins to contract, in order to keep the same total energy, the temperature must increase. In order to keep the same energy, the temperature must increase. Remember, energy is the total energy of particles, or thermal energy is the total energy. Temperature is a measure of the average energy. So, in order to keep the total the same, if we're getting smaller, the temperature will increase. And of course, the places with more mass are going to be hotter in order to keep that energy the same. We've already determined that the center is the densest part. The densest part has more mass, more matter, and therefore going to have the highest temperature. So the temperature is going to rise in the center. It's going to be cooler towards the outer edges. And of course, condensation sequence theory says that the temperature varies from inside to outside. And this is just a part of it. Mostly it's a conservation of energy. So big cloud, shrinking because of gravity, spinning because of conservation of angular momentum, flattening because of collisions from conservation of angular momentum, heating up towards the inside because of conservation of energy, and temperature varying due to the condensation sequence theory. So far, everything's going right along what we would expect. But then there comes a problem. Okay, we've talked about that we should have planets orbiting around some center, but why would we end up having two major types of planets? Well, let's look at that. In the universe, and the solar system specifically, 98%, if not 98.9%, of all matter is either hydrogen or helium. Most stuff is hydrogen or helium. But the thing about hydrogen and helium is no matter how cold it is, they will never become solid, ever. They will only even become liquid under pressure. So they're always gases. Next, we got about 1.4% of the material in the solar nebula are those hydrogen compounds, those ices. NH3, CH4, H2O, water, methane, ammonia. That's over right? I did. That's about 1.4% of the material. And if the temperature is less than 150 Kelvin, no pressure, meaning not in any atmosphere, they will freeze. So it has to be pretty cold to get these things to freeze solid. Rocks, which make about 4% of the material, they're almost always solid. From a temperature of 1300 Kelvin, which is super hot, to about 500 Kelvin, they're going to be in that solid state. So it doesn't even have to be cold for them to condense. And metals, of course, which only make 0.2% of the material in the solar nebula, it can be up to 1600 Kelvin, so really hot, and they'll condense. Now what does that mean for us? This creates the idea of the frost line. Because of the way the solar system is heating up, remember it's hotter towards the center. Here, this is hot. And then we're going to make some line called the frost line. And beyond that frost line, it's cold enough for those ices to condense. So the water's methane ammonia, it's cold enough beyond this frost line for those ices to condense or freeze. The hydrogen here, helium is not going to condense anywhere. But in here, in this hot zone, quote unquote, rocks can condense, metals can condense, but that's it. Out here, rocks can condense, metals can condense, and those ices can condense. Okay. If only rocks and metals can condense, meaning freeze, there's not as much material to grow solid planets. Meaning as the planets begin to clump together, it's going to be metals and rocks that are clumping together. And there's not a lot of that. 0.2%, 0.4%. So a total of 0.6% of material is available to make a planet out of. So we're going to end up with like smaller planets because there's less stuff. But then we go outside the frost line, where those waters, methane, and ammonias, those ices can condense. That means there's a lot more stuff to grow planets out of, right? That's 1.4% of the material can be made planets out of. And not only that, because these planets were able to form larger, denser, more gravitationally affected cores, it was able to attract some of that hydrogen and helium, right? In here, it's really volatile. So we got smaller cores, harder to hold on to that hydrogen and helium. Here we've got larger cores, cooler temperature, easier to hold on to that hydrogen and helium. So we would get larger planets out of here, composed mostly of gas, and we would get smaller planets here, comprised mostly of rocky materials. So we want to look for observable evidence out there in the universe. We want to look for other areas that look like new solar systems forming. Let me tell you about the nomenclature really quickly. Since our sun is our star, it gets the name sun, right? And so describing a solar system technically speaks only about our solar system. If we were around another star, that star would be our sun, so that would be our solar system. So technically, we should refer to these as planetary systems, since that star is not the sun. But you all know what I'm saying when I say solar systems. So we're looking for stars with disks of warm material around them. And we find that. It wasn't until absolutely recently we were able to detect specifically planets, but we were able to see stars, or young diffuse protostars with disks of warm material around them. just as we think our solar system would have been at one point when it was young. A really intense computer model had a diffuse cloud of gas. We ran it for a while and eventually got to a point where it had 100 planetesimals orbiting the sun. So this is just a star with the sun's mass, and each one of these has random masses. And we put them in random orbits. Sorry about that. And we ran it for 30 million years, and after that, 100 planets had coalesced into 22 planetesimals. So they're all orbiting. Some of them are larger, some of them fall into the sun, some of them collide. And after about 441 million years, we only get 4 planets left. And they seem to be moderately stable, except these two seem to like, that's pretty close, but they seem stable at that point. So the computer model evidence says that our hypothesis may still be correct. So it's still valid so far. Sometimes people use Jupiter and Saturn as quote unquote miniature solar systems. Excuse me. And have the moon systems mirror planetary systems because of how many moons they have. Of course, it doesn't directly correlate because Jupiter and Saturn aren't stars. But it still shows trends of like density from inside out. So there are some similarities that we can investigate using the Jupiter system or the Saturn system. An interesting thing about the moons of the Jovian planets is they also form in accretion disks. So for instance, this is the solar nebula, and this is Jupiter's accretion disk, meaning that Jupiter is forming within this. And then we've got the smaller moons forming throughout that. Okay. And this is just a slide showing those disks around other stars that help support the hypothesis. Like I said, none of this is proving the hypothesis, but it is all supporting the hypothesis. So as long as we can find evidence supporting it, we can keep going. So one of the things we've learned is that galactic recycling, so what that means is that you have a star, it lives, it burns all of its hydrogen, then it starts to fuse its helium, and when it goes supernova, it releases heavier materials, which might help to form planets during its next quote-unquote cycle. And of course, we can absorb these forming in other gas clouds. Do y'all have any questions? Seems pretty straightforward. I have a recap here, so the last few slides are just a recap. The first one says, where did the material come from? That's that galactic recycling. This asks what caused the orderly patterns of motion. Don't forget, we had the large cloud of gas. It shrank because of gravity, spun faster because of angular momentum, heated up because of conservation of energy. And don't forget those collisions that caused it to flatten into a disk. Don't forget the terrestrial planets were formed inside the frost line due to the smaller amounts of solid materials from which to form planets. Outside of the frost line, the hydrogen was able to accumulate around those ice cores that could be formed due to the large amounts of available ices that can condense. The next question I want to start talking about is where did the asteroids and comets come from? But I think I want to do that next week. So that's it for today. Hopefully you all got something out of it. I really like talking about the formation of the solar system. It's super interesting. Not just from an aesthetic standpoint, but the science of it is, in my opinion, very hot.